Hello, this is going to be a video on the mean value theorem, which branches off of the Rolle's theorem and the extreme value theorem. So the mean value theorem says, suppose y equals f of x is continuous over a closed interval ab and differentiable on the interval's interior ab. Then there is at least one point c in ab at which, and this part down here, f of b minus f of a over b minus a equals f prime of c. What that means is really just the slope between the points a, b is equal to the derivative of the graph at some point c. So basically just like the slope or the average rate of change of the interval from a to b will be the same gradient or slope at a derivative tangent at some point along that graph, if it follows all the rules above. So I'm going to be proving that as well. So to prove it, over here on this right side here, I made a little bit of a picture. And what the picture shows is a graph f of x, a graph g of x, and h of x. Now, what you should notice first is g of x here, I wrote down here, and I wrote it as a function. And basically, I wrote it in point slope formula. So this isn't super complicated. Each part here is just components of point slope formula using a and b as the interval points. So I have, this is just slope right here, this kind of long bit, and then everything else is just going to be the point slope formula. So don't get too wound up in that. Not very complicated. But anyways, I also wrote down here h of x. Now, h of x is the difference between f of x and g of x. So I could write h of x as being equal to f of x minus g of x. Not the best g. Minus g of x. Okay? And what we know up here is that g of x is equal to all this. So what I'm going to do is I'm just going to substitute g of x out right here and put in what it's equal to, which is going to be all of this right here. I'm just going to copy and paste that, put it right here. There. Okay, so now what we have is this equation where we have h of x is equal to the difference between f of x and this long part here. Now what I want to show you is take note of h of x here. Now, if you remember the extreme value theorem and Rolle's theorem, the extreme value theorem basically just says on a closed, fully continuous interval where the endpoints are defined and included in the interval, there will exist a minimum and a maximum value. So in other words, there must be a maximum and minimum value on h of x, because we already know that since f of x over here in this theorem we wrote, since f of x is continuous over a closed interval, and g of x is just a line, a straight continuous line in that interval that is defined on both a and b, then the difference between them is also going to be continuous and differentiable. So we can say that h of x fits the extreme value theorem. And in other words, we know for sure that there's a minimum and a maximum. In this case, we have this maximum value at some point c. And our minimum values are going to equal 0 here, because if you notice, the difference between f of x and g of x will be 0 when they're touching, or when they're at a and when they're at b, they're equal to one another, so you'll know it's 0. So in other words, f of a equals f of b. And so bringing into Rolle's theorem here, we know that there must also be, given that the extreme value theorem applies, there must also be a point on this, which in this case is point c, where the derivative is 0, or a 0 slope tangent, which is at h of c. So I'm just going to write h of c. And in other words, h prime of c, or the derivative, that's just there, is equal to 0, using the Rolle's theorem and the extreme value theorem. Hopefully that made sense. Take note, though, that this 0 occurs at the peak or at the extreme value. So in other words, the point at which f of x and g of x are the furthest apart, because h of x is the graph of their difference. And so when it's at its maximum value of h of x, then it's also going to be the most difference between the two graphs. So just take note of that. I'm going to put this in the top right corner up here just to hang on because I'm going to get to it in a minute. Now what I'm going to do is I'm going to take the derivative of this entire graph or function I made down here. And since I'm kind of running out of room, I'm going to write that over here on the left side. And so what that's going to be is h prime of x is equal to f prime of x minus f of a is a constant, so it will be 0 plus, and then this term right here, f of a minus f of b over a minus b times x minus a. The derivative of x minus a is just going to be 1 because a is a constant and x is just a power of 1. So that will be a constant times, or well, I'm sorry, it'll be a constant times the derivative of x, which is just going to be the constant. So it's just going to be f of a minus f of b over a minus b. I'm just going to copy that and put it right here. So that's that part. And now what we have is we're going to evaluate this at the point C. And remember up here in the top right, we know that h prime of c equals 0. We talked about that earlier. So I'm just going to say 0 equals, and then we're evaluating f prime of c. And then minus, and then we have all of this again. Okay, let me just move all this down. I'm running out of room. There. Okay. Now what you'll notice, hopefully, is we can just rearrange this by adding f of a minus f of b over a minus b to both sides. And we'll actually get this part right up here. So in other words, I can just take this, copy, paste, boom, right here. Just by rearranging, just by adding to both sides, which is the proof for the mean value theorem. And just to stress a little bit more, basically what this is saying is, I kind of already wrote this here. The slope of the graph g of x will be the derivative at some point c on f of x. That's basically what it's saying. And you can just kind of visualize it by saying that slope right there, it's going to be a parallel line, which you can see I already drew here, but it'll be a parallel line to g of x. And so this kind of doesn't really involve any formula that we need to use. This is kind of, it's not really complicated. We can just say that we're solving for the value like we would always do. We could just find the derivative, the formula for the derivative, and then set it equal to whatever value we want. It could be 0, it could be 1, it could be 2. But now we're just kind of proving that those values will exist. Another way to look at it is if you're dealing with velocity, a way I like to think about it is say that the average velocity between points A and B here, say the average velocity is 60 miles an hour. So the mean value theorem would say that because the average or the slope is going to be 60 miles an hour, then there must be at least one point on the graph of s of x, where s of x is position. It'd be s of t, position and time, in terms of a physics graph. It's saying basically that some point on that graph, the derivative will actually be 60 exactly, which is interesting. It could happen more than once. Again, like you could have multiple points at where g of x is the same slope as tangents multiple times. But that doesn't really matter. This is just more of a proof of it. And hopefully that helped anyone understand it a little bit if they needed a little bit of an explanation. If you think I could explain it in another way, or you need me to clarify something, or maybe I didn't explain it the best way, let me know, and I will try to cater to your needs. Just drop a comment or something. I'll try and respond to it. But that's just going to do it for the mean value theorem.